In section 4.5, we will talk about the dimensions of a vector space. We say that the dimensions of a vector space is just the number of vectors in the basis for the vector space. If a vector space has a basis with finite number of elements, we say that V is finite dimensional. And we say that if a basis is not finite dimensional, then it is infinite dimensional. Let's look at some examples of finite and infinite dimensional vector spaces. We will begin with the dimension of R3. If we look at the standard basis for R3, we have the basis equal to E1, E2, and E3. And by definition, the dimension is just the number of vectors in my in my basis. And so the dimension here would be 3. Likewise, the dimension of Rn, if we look at the basis here, which is E1 through En, my basis would be equal to n. If we look at the dimension of a polynomial p sub n, in the general form here, my basis is 1x, x squared, excuse me, up to xn. So therefore, we notice that the dimension here would be n plus 1. Again, the dimension is just the number of vectors in my basis. A few examples of infinite dimensional vector spaces. We have dimensions of FR, which is the set of all functions. And if we have C of R, this is the set of all continuous functions. And then if we have D of R, this is the set of all differential functions. All of these have infinite bases, and therefore we say are infinite dimensional. So if V is n-dimensional, then the basis for V has only n vectors. And we have a theorem. If V has a basis equal to B1 through Bn, then any set in V containing more than n vectors must be linearly dependent. Let's think about why that is true. If we add more vectors to this basis, of course, to have a basis, we have here, it has n elements in it. And if we have more than n elements, of course, here to form a basis, all these vectors B1 through Bn must be linearly independent. So if we add any additional vectors to this, then of course it has to be linearly dependent, because anything we add will have to be a scalar multiple or some linear combination of what we already have in the basis. Okay, so again, our basis, we know that all vectors must be linearly independent. And so it's the set of all of linearly independent vectors. So any that we add that is more than n, well, of course, will be dependent. Otherwise, it would have originally been in the basis. And then lastly, theorem says that I let all bases of a vector space V have n elements. So now let's look at an example. We want to find the dimension and basis for this subspace S, which spans the 3 vectors that are listed. So if we let our A equal to the matrix of the vectors, then what we want to know first, does this A equal to 0 have a non-trivial solution? Okay. And so how do we find that out? We need to put this matrix into REF. Putting this matrix in row echelon form, we see we have a pivot here and a pivot here, and so we have two pivot columns, and these two pivot columns form a basis for the set S. So we have B is equal to the 1, 1, 1. Of course, we go back to the original matrix, and then 2, 1, negative 1. And so this forms a basis for this set S. And then we are asked for the dimensions of S. And the dimension of S is just the number of vectors in the basis. So we have 1, 2. So the dimension of this S, this subspace S, is equal to 2. Now let's find the dimension and basis for this subspace H. So we notice we can write this space as A times the vector 1, 1, 0, was given here, and plus B times the vector negative 2, 1, 3. So we know that this H spans these two vectors, but we must check to see if these two vectors are linearly independent and if they also form a basis. So making an equation, not an equation, excuse me, making a matrix with our vectors and putting it into row echelon form, we notice here that we have a pivot in every column. And so therefore, we see that these vectors are indeed linearly independent. So a basis is indeed these two vectors because they're linearly independent. And so if we want the dimensions of my space, there are two vectors in my bases, so the dimension is equal to 2. Now let's find the dimensions and basis for this subspace H. So we notice this H is equal to this linear combination as listed. And so if we call these vectors V1, V2, V3, V4, of course we know that these columns, these vectors span the space. But the question is are they linearly independent? And if you notice, let's look at V3. V3 happens to be negative 2 V2. And so therefore, since V3 can be written as a linear combination of the other vectors, then we can remove this vector from our space, and we get that our basis is equal to 1, 5, 0, 0, negative 3, 0, 1, 0, and 0, 4, negative 1, 5. So therefore, our dimensions of H would be 3. Now, what you might notice is what if you don't recognize that V3 happens to be a linear combination of the other vectors, or it's something that's not so easily seen. So what will we have to do in that case? If we don't see right off that V3 is a scalar multiple of V2, then we have to put our matrix. So we look at our matrix here, and then we notice we put it in REF, and we notice that we have 3 pivots. And so here, this is a non-pivot column, and so the columns where we have pivots, 1, 2, 3, will then, from our original matrix, form the basis that we had before. And again, we will see that dimensions of H indeed is still 3. Sometimes we may need to extend a set to form a basis. That brings us to a theorem. Let V be an n-dimensional vector space with subspace H of V. Then 1, any linearly dependent set S in H can be expanded to form a basis for H. And then the dimensions of H will be less than or equal to the dimensions of V. So given this set X, we want to extend the linearly independent set to form a basis for P2. So we see set S, we rewrite the set S, and we want to expand this set S by including the standard basis for P2. So we will include the vectors 1, x, and x squared. And keep in mind, as we remember, that this is the standard basis for P2. So of course we can write this in vector form, and writing this in vector form, here we would get 1, I guess that should probably be a -1, sorry. We get -1, 0, 1, and then we'll get 3, -2, 0, and then my standard basis will be, of course, 1, 0, 0. I'm running out of room, and so it will be 0, 1, 0, and 0, 0, 1. Okay. So we know it spans this set. And so now if we put this into a matrix form, we just want to put this into REF. And by putting this in the REF, we can find out what our pivot columns are and form a basis. Putting this into row echelon form, we get these 3 pivot columns. And so therefore, our basis is -1, 0, 0. Ooh, that is not true. What should it be? We should go back to our original matrix, right? And choose these vectors. And so therefore, we have -1, 0, 1, 3, -2, 0, and 1, 0, 0. And we've seen why it is not always true that the reduced form will form a basis. We saw that in the last section, or maybe a couple sections ago. And so therefore our basis comes from our original. So now if we want to find the dimensions of S, we see that it is 3 because we have 3 vectors in my bases. So we have a basis, the basis theorem. And the basis theorem says if V is a p-dimensional vector space with p greater than or equal to 1, then 1, any linearly independent set S in V with p vectors is a basis for V. Also, 2, any set S in V with p elements that spans V is also a basis for V. Now I want to talk about the dimensions of null of A and column of A. So it's actually easy to find these things. And so we find that once we put it into row echelon form, that the dimensions of null of A just happens to be the number of non-pivot columns of A. And the dimensions of column of A happens to be the number of pivot columns of A. And so, of course, if we were to add the dimensions of null of A plus the dimensions of column of A, it will equal to the total number of columns in A, because of course non-pivots plus pivots will make up the total number of vectors in A, columns in A. And we'll actually see in our next section, we'll use this terminology, the nullity is going to be equal to the dimensions of null of A. And we'll talk about the term rank, which is the dimensions of column of A, and so therefore rank plus nullity, of course, will equal the total number of columns. So, for your reading assignment, I would like for you to define dimension, as well as define the dimensions of null of A and the dimensions of column of A. So define dimension, define dimensions of null of A and the dimensions of column of A, and then I would like for you to find it for this matrix A. Keep in mind this is actually a simple task. We want to start by putting this in row echelon form. Once we have it in row echelon form, we can find out our pivot columns, and of course, by definition, our pivot columns will be the dimensions of the column of A. And then we find our non-pivot columns, and the number of non-pivot columns will give us the dimensions of the null of A. So put this in REF. You should be able to do it by hand. If not, you're welcome to use software.